Next time you're walking down a city street, stop for a second and just look straight up. From the concrete of the sidewalk, modern mega-skyscrapers look absolutely invincible to us. They appear as these monumental structures of pure, motionless strength, just absolute monoliths of steel and glass, securely and permanently planted in the sky. But the reality is far more dramatic than what we see from the ground. Right now, at the very top of the world's tallest buildings, a constant, incredibly violent structural struggle is taking place. You see, these towering giants hide an invisible, relentless war against the natural elements. It's a war fought every single second of every single day, completely out of our sight. So the pivotal question we really have to ask is, how exactly do these megastructures survive? Because nature, especially at these extreme, dizzying altitudes, is definitely not just some passive, pretty backdrop for human architecture. Nature is a relentless, punishing antagonist. Now, we often assume that massive earthquakes are the primary threat keeping structural engineers awake at night, but the truth is actually quite different. Engineers are constantly designing for a much more frequent, persistent, and terrifying force, a force that literally never sleeps. Down here at ground level, wind usually just presents itself as a gentle, harmless breeze. It's broken up by trees, houses, and the natural terrain. But hundreds of meters up in the air, completely devoid of any ground friction to slow it down, the wind behaves like an invisible, crushing ocean. We're talking about staggering velocities. It slams into structural glass and steel panels with immense, highly concentrated pressure, testing the absolute limits of modern metallurgy. It is a profoundly violent sky up there, a chaotic storm of invisible kinetic energy, and just surviving it requires nothing short of brilliant, world-class engineering. In this explainer, we're going to uncover the structural secrets keeping these buildings upright. We'll look at the rigidity paradox, the hidden danger of vortex shedding, the geometry of confusion, anchoring towers underground, and finally, the giant mechanical counterweight. Let's dive right into part 1, the rigidity paradox. This is where human intuition completely clashes with the unforgiving laws of physics. We naturally tend to think that for something to be strong, it has to be entirely stiff and unyielding. But in skyscraper engineering, brute rigidity is actually a fatal flaw. Think about it. If a building was constructed to be perfectly stiff, the sheer physics of that high-altitude wind pressure would cause the rigid materials to snap directly at the base foundation. Millions of tons of steel and concrete would literally break under the strain. So, to prevent catastrophic failure, a skyscraper absolutely has to flex. The tallest modern structures in the world are intentionally designed to act almost like massive trees in a violent storm. They are engineered to gracefully bow and sway, sometimes up to several feet in either direction. By dynamically absorbing those immense atmospheric forces, they survive. Which brings us to part 2, the danger of vortex shedding. Now, allowing a building to bend solves that initial crushing wind pressure problem we just talked about, but it introduces a whole new, deeply dangerous aerodynamic paradox. When powerful wind currents slam into a high-altitude structure, the airflow splits violently at the hard architectural edges. As this fast-moving air passes down the sides, it forms localized, swirling whirlpools of air. Engineers call these vortices. And here's the terrifying part. These vortices detach in a rapid, alternating pattern. Left side, then right side, then left again. This creates a rhythmic, low-pressure pull that physically yanks the building side to side, perpendicular to the actual direction of the wind. If this rhythmic timing happens to match the building's own natural frequency, the swaying amplifies rapidly. It causes severe motion sickness for anyone trapped inside, and it introduces an immense structural fatigue that can literally shake a multi-billion-dollar tower apart from the inside out. So how do we stop it? Let's look at part 3, the geometry of confusion. To stop the lethal threat of vortex shedding, engineers don't just lazily add more heavy metal bracing. Their very first line of defense is actually far more elegant. It's geometry. You see, a traditional square tower is basically just a giant sail. Its sharp, flat, linear surfaces catch the wind perfectly, which creates those highly dangerous alternating whirlpools. But a modern twisted tower features a highly calculated aerodynamic profile. It is physically designed to confuse the wind currents. By avoiding simple square boxes and flat vertical walls, these modern towers actively disrupt the formation of those swirling vortices. They break up the wind's organization, safely guiding the massive air currents right around the structure. Think about this number for a second. 24. That is the staggering, incredible 24% reduction in total wind forces achieved simply by the structural design of the Shanghai Tower. Nearly a quarter of nature's crushing force, completely neutralized, without adding an ounce of extra steel, simply because of the building's shape. Let's look a bit closer at how specific architectural marvels actually pull this off. The Shanghai Tower, rising high into the sky, uses a precise, sweeping 120-degree aerodynamic twist. Like a sculpture crafted by pure mathematics, this twist continuously breaks up the dangerous vortices as the wind desperately attempts to climb its height. Over in Dubai, the Burj Khalifa utilizes a changing, spiraling, stepped footprint. Because the building presents a completely different shape and profile at every single height interval, the wind can literally never organize itself to create a synchronized, devastating push. And the Shanghai World Financial Center takes a different approach. It leaves a massive, open, trapezoidal aperture at its peak. It's a giant, engineered void that allows powerful, high-altitude wind streams to simply pass straight through the top of the building completely harmlessly. They aren't trying to fight the overwhelming power of the wind. They're elegantly manipulating nature's force, guiding it away. Moving on to part 4, anchoring massive towers underground. We've spent a lot of time looking up at the violent sky, but we absolutely have to pivot our attention deep down into the earth. How do these ultra-tall, unimaginably heavy structures avoid simply tipping over or sinking under the massive, crushing force of their own gravity? Well, the secret lies completely out of sight, down in the subterranean darkness. In cities with soft soil, like Chicago or Dubai, you can't just sit a massive building on top of solid bedrock. It doesn't exist near the surface. Instead, engineers drilled dozens of massive concrete pillars, hundreds of feet straight down into the dirt. These are called friction piles. And the counterintuitive reality here is that it's actually not the tips of the pillars resting on deep rock that hold the building up. It is the surrounding soil itself, tightly squeezing the sides of the concrete shafts. The claustrophobic, immense mechanical friction of compressed earth pressing endlessly against the surface area of the concrete ensures the entire skyscraper cannot sink, tilt, or shift even a single inch. And finally, part 5, the giant mechanical counterweights. Even with perfect aerodynamic geometry reaching high into the sky and deep subterranean friction piles fiercely gripping the earth below, these massive structures still face ultimate, catastrophic threats. Extreme typhoons, Category 5 storms, and deep seismic earthquakes pose a truly lethal danger. The solution? Engineers created a silent monster, hidden right up in the attic of the building. 660. That is the mind-bending weight, in metric tons, of a giant spherical steel pendulum suspended on the 87th floor of Taiwan's Taipei 101 Tower. This immense, awe-inspiring device is called a tuned mass damper. Hung near the very top of the skyscraper's dark interior core and suspended by remarkably thick steel cables, this massive golden sphere utilizes the simple, unyielding physics principle of inertia. Here's how it works. When a violent typhoon or a massive earthquake forcefully tilts the towering structure to the right, inertia dictates that this massive steel ball resists immediately moving with it. It effectively pulls back toward the left. It acts as a gigantic stabilizing counterweight, pushing in the exact opposite direction that the building tilts. As it swings, it absorbs the building's highly dangerous kinetic energy, rapidly dampening that lethal, high-altitude swing. And this isn't just theoretical physics either. It is a brilliant system that has been put to the ultimate high-stakes test. Let me paint a picture for you. In the year 2002, a massive 6.8 magnitude earthquake violently struck Taiwan. Milliseconds later, the ground shifted forcefully and the upper floors of Taipei 101 began to dangerously, heavily sway to the right. But just 1 second later, that massive steel ball resisted via inertia. It silently pulled to the left with hundreds of tons of counterforce. Within 3 seconds, the violent movement was dampened. The tremendous kinetic energy was absorbed entirely, keeping the entire towering structure completely, perfectly secure, while the earth literally violently shook below. So it really is a silent war, fought entirely with brilliant engineering. The high-altitude winds and the deadly phenomenon of vortex shedding, they're permanently neutralized by aerodynamic geometries, carefully calculated twists, and massive architectural apertures. The unimaginable weight and the looming threat of sinking in soft soil, countered by the deep, crushing friction of subterranean piles. And the extreme, violent swaying caused by earthquakes and massive typhoons, it is kept tightly in check by massive hidden tuned mass dampers, silently swinging in the dark. Mega skyscrapers don't survive because they are simply stronger or more rigidly built than the raw natural elements around them. As we've seen, that would be a fatal mistake. They survive because they are engineered to be infinitely smarter. They elegantly guide force away rather than stubbornly fighting it head-on, which leaves us with this final, profound thought to consider. When we build these incredible, gravity-defying monuments thousands of feet into the sky, are we truly conquering nature? Or are we simply learning how to dance with its invisible, terrifying forces? It's definitely something to think about the next time you find yourself looking straight up at a towering city skyline. Thank you for joining me for this explainer. I really hope it has completely changed the way you view the architectural giants silently living all around us.